Good afternoon, everyone. My name's Maria, and today I'm going to talk to you about my PhD research looking at proximal sensing in soil water repellency management. So water repellency, as I'm sure we all know, is quite a significant agricultural issue in Western Australia and Southern Australia. And it basically inhibits water infiltration throughout the soil surface and down the soil profile. It's particularly prone to these sandy soils, which we have in WA. So my research centred around two main thesis aims. Firstly, we wanted to see whether climate and soil properties influence water repellency and how climate modifies these relationships between water repellency and soil properties. Secondly, we know water repellency varies quite a lot spatially and over different scales. So we wanted to see whether proximal sensors can support its management over different managing things and climate scenarios. So firstly, we conducted quite a comprehensive literature review, which is published in the Sandy Soils book as a book chapter. And we looked at whether proximal sensing is a viable option in managing water repellency. So we had a few significant findings from this. So current water repellency management is costly and inefficient. It's usually done in a blanket or uniform fashion, which is quite expensive to do for the farmer. Water repellency does have a strong spatio-temporal variability across farm and different scales, and geostatistical studies do show a scale-dependent pattern. Therefore, proximal soil sensors do offer a solution. So firstly, we wanted to assess the effects of both climate and soil properties on water repellency. So we know there are already established relationships between soil properties and water repellency. So generally with increased organic carbon comes increased water repellency, and increased clay usually less water repellency. So this study is currently published in Katina, and we had a few findings from this. So soil properties are the main drivers of water repellency. This is mostly organic carbon and soil texture, but climate, in particular mean maximum temperature, does modify this. We found hotter conditions or warmer conditions reduce water repellency and weaken the role of soil organic carbon in causing water repellency. We found that to have accurate water repellency models and risk maps, they must include both soil and climate variables. We also found that water repellency occurred over a range of soil textures as long as organic carbon thresholds were high enough. Therefore, soil carbon farming projects may unintentionally increase water repellency risk. Secondly, we wanted to look at whether proximal sensing was a viable option to predict water repellency at the farm or paddock scale. We used a range of sensors, so Vis-IR spectroscopy, gamma radiometrics, and electromagnetic induction. And we found they actually had poor predictive power by themselves to predict water repellency on farm. However, Vis-IR did show some promise, and it revealed key spectral signatures for both organic carbon, clay, and water repellency. Sensor data fusion, so combining the three sensors together, improved prediction of some properties, mostly organic carbon, clay, and iron, but not water repellency. We found that soil type and measurement depth constrained this. So key takeaways and next steps. Water repellency is primarily controlled by soil properties, mostly organic carbon and texture, but climate does have a significant effect, particularly mean maximum temperature. Sensor fusion, Vis-IR, gamma, and electromagnetic induction poorly predicted water repellency. However, Vis-IR did show promise by detecting hydrophobic functional groups, which are directly related to water repellency. Localised calibration and scale-aware approaches are needed for accurate water repellency mapping, and future work would be to develop water repellency spectral libraries, perform field-based Vis-IR and MED measurements, and also integrate both proximal sensing and remote sensing. And I'd like to acknowledge these following people. Thank you.